Welcome to Grade 11 Physics. We're starting with Unit 1, Kinematics. Kinematics is defined as the study of motion. It comes from the Greek word kinema. In this unit, we will be studying moving objects. We won't be concerned with why the objects are moving. That discussion will happen in Unit 2 when we study dynamics. Before we begin, we need to introduce the concept of scalar and vector quantities. All measured quantities in science are classified as either a scalar quantity or a vector quantity. A scalar quantity is a quantity that has only a magnitude or a size. Examples of scalar quantities are time, example, 5 seconds, mass, example, 5 kilograms, and speed, example, 5 kilometers per hour. Each of these quantities has a magnitude or a size and a unit. A vector quantity, on the other hand, is a quantity that has a magnitude and a direction. So there are two components to a vector quantity. We have the magnitude and the direction. These quantities may be part of your vocabulary, but you might not have any experience studying or doing calculations with them, as we introduce them to you for the first time in Grade 11 University Preparation Physics. One example of a vector quantity is velocity. Example, 5 meters per second north. Second example of a vector quantity is acceleration. An example would be 5 meters per second squared north. We're going to talk about each of these quantities in much detail when we study kinematics this unit. Let's start with our first quantity, which is distance. Distance is defined as the total length of the path traveled by an object in motion. The symbol for distance is the Greek letter delta and the lowercase d. And the unit of measurement for distance is the meter. And the symbol for this SI unit is a lowercase m. Distance is a scalar quantity. Let's take a look at this example here. Here we have a house and a school. And the student walks from his house to the school following this path. So if you notice, it's not a straight line, but if you were to measure the distance of this path length, you would have the distance traveled. So let's just label this. This, my friends, is the distance traveled. Okay. The second quantity that we're going to look at is called position. And position is defined as the distance and direction of an object from a reference point. Now, because there's a direction, this is a vector quantity. And whenever we describe vector quantities, we give them special embellishments so that when we look at the symbol for a vector quantity, we know right away that we're talking about a vector. So the symbol for position is the lowercase letter d, but it is embellished with an arrowhead on top. Whenever you see an arrowhead on top of a quantity, you know right away that we're talking about a quantity that has both a magnitude and a direction. Another way to denote a vector quantity is by just having a straight line on top of the symbol. So we could also write position like this, D with a straight line. Some textbooks will denote vector quantities as a bold letter. I'm realizing now that I probably should have typed these letters in so that you can see them, but that's my best way to represent a bold letter. If it's a bold letter, it doesn't need an arrowhead or a line on top. The bold letter itself will actually denote that it is a vector quantity. Alright, the unit of measurement for position is also the meter, and we use the symbol m. An example of a position would be 300 meters east of home. So, in a position, we have things that you need to be aware of. We have the magnitude, we have direction, but for position we also have this third part here, which is called a reference point. 300 meters east does not tell us exactly where that person can be found or that object can be found. But if we put in a reference point, such as the home that we're starting from, then we know exactly where that person is. We can identify precisely where the position of that person or object is. Okay, the third quantity that we're going to look at today is called displacement. And displacement is defined as the change in position of an object. The symbol is delta D with an arrowhead on top. So we know that D with an arrowhead on top means position. If we put a delta in front of it, whenever there's a delta in front of a symbol in mathematics or science, it means the change in. So that delta sign means change in. So you can actually read this, it's change in position, which is the definition of displacement. So the symbol for displacement is delta D with an arrowhead on top. And the unit of measure is also the meter. If we look at our example where the student traveled this curved path to get to school, we could define the displacement as the change in position. So position number 1 is right here, home. We'll call it the initial position. And position number 2, or the final position, is the school. This person changes their position in going from home to the school. This straight line path with the direction tells you the displacement of the object or individual. It's the change in position. He started here and ended up here. So displacement is the straight line distance between these two, and we give it the symbol delta D with an arrowhead on top. Okay, there are two equations for displacement. And which one you use depends on what quantities are given in the question itself. And don't worry, we're going to practice all the different possibilities. The first equation says that delta D is equal to D final minus D initial. So delta D is equal to D2 minus D1. In order to use this equation, you have to have positions given to you in the question. The second equation to find displacement is not really much of an equation. Basically, what it's saying is the total displacement is equal to the sum of the displacements. So if in your question they give you displacements and you want to find the total displacement, just add them up. Okay? So we'll do some examples that use both of these. But before we do, we have to learn some rules for adding vector quantities. Vector quantities cannot just be added like regular numbers. They have to be added using a special rule because they have a direction incorporated with them. Okay, so let's take a look at these three vectors. We can represent a vector with a straight line with an arrowhead showing direction. So this first vector, which I'm going to label A, this one is B, and this one is C, is a displacement of 7 kilometers, and it's pointing east. So we have delta D is 7 kilometers east. Now take a look at vector B. We can see that vector B is pointing in the opposite direction. So vector B is pointing west. Now that's not what's written. What's written is displacement is equal to negative 7 kilometers east. Now this is important. Whenever you have a vector with a direction, you can change its sign. So I can change this from negative to positive 7 kilometers. But when you do, you change its direction. So changing the sign of a vector changes its direction. So we change negative 7 kilometers east is the exact same thing as positive 7 kilometers west. Now, why would we even attempt to write this as negative 7 east when we can clearly see that this vector is pointing west? Well, the answer to that is really visible when you see what happens when you add and subtract vectors. And there are special rules, so that will end up being a trick that will actually save you and allow you to solve these problems. So if we look at vector C, we can see that it's pointing east, but instead of writing it as east, they've written it as negative 7 kilometers west. So let's rewrite this as positive 7 kilometers east. Negative west is the same thing as positive east. Okay. So, returning back to our note, adding vector quantities. The method by which we add vector quantities depends on whether the vectors are collinear or non-collinear. So what does that mean? Well, first we're going to look at adding collinear vectors. They're the simplest type. A collinear vector is described as any vector located along the same straight line. So east and west are located along the same straight line. So we can say that east and west are collinear. Vectors that are collinear can be in the same direction. If they are pointed in the same direction, they are called parallel vectors. I want you to take a look at vectors A, B, and C. Which of these three vectors are pointed in the same direction? You can see that vector A and vector C are both pointed east, so A and C are parallel collinear vectors. Then let's take a look at vectors that are pointed in opposite directions. If they're pointed in opposite directions, then we say that they are antiparallel collinear vectors. So, vectors A and B are pointed in opposite directions. So, A and B are collinear but antiparallel. B and C are also collinear vectors because they're pointed along the same straight line, but they're in opposite directions, so B and C are also antiparallel collinear vectors. If you have collinear vectors, there's a rule on how to treat them mathematically. And I'm going to place this rule behind these bars of memorization. I'm going to put these red lines on the left and right hand side of any concept, term, or definition that I think is important for you to remember, or when flipping through your notes to be able to recall because it's an important quantity or an important concept. So I use the bars of memorization to highlight any important points. This rule tells us what to do with collinear vectors. Collinear vectors are added algebraically. And what that means is they're added just like you would regular numbers. When added algebraically, all vectors must be expressed in the same direction. And that's the key point right there. You cannot add two vectors if their directions are not the same. The best way to highlight this point is by doing an example. We're going to start with sample problem number 1. I'm excited for you guys because this is your first physics problem ever. Imagine you walk from the school 500 meters east of home to the library 1,200 meters east of home in a straight line route. What is your displacement? So you can look at the diagram below and you can see where you started from the school. This is your initial position right here. And you end up going to the library right here. And what we want to find is our displacement. When studying any problems in math or science, we use a method called the GRASP method. G-R-A-S-P. And the very first part of the GRASP method is the most difficult part for any problem-solving question that you can attempt at any level. And that is just identifying what's given in the question. So G stands for given. We want to read this question and use reading comprehension to identify what's given in the question. So I'm going to read and I'm going to highlight all of the information as I go along. Imagine that you walk from the school 500 meters east of home to the library 1,200 meters east of home in a straight line route. What is your displacement? So we're given two quantities. The first one is 500 meters east of home. This quantity has a magnitude, a direction, and a reference point. So it must be a position and is given the symbol D with an arrowhead. More importantly, this is our starting position. So this is our initial position. We can give it the symbol D1 or DI, whichever you prefer. So we're given our initial position, which is 500 meters east of home. Next we have 1,200 meters east of home. There is a magnitude, a direction, and a reference point. So this too must be a position. It is, more specifically, our final position. Just reading the question and identifying what is present in the question is the single most difficult part of answering any problem-solving question in math or physics. Okay. The second part of the GRASP method is identifying what is required. And though this may seem easy, this is the second most difficult part of any problem-solving question. Just identifying what's required, what they're asking you to find. So if you read this question, you can see that they're asking you to find the displacement. What is your displacement? The symbol for displacement is delta D with an arrowhead on top. So we're given initial position, final position, and we need to find our displacement. The third part asks us to analyze which equation we will use. So we have two equations for position, one which we can use if two equations for displacement rather, one which we can use if we're given positions, and one in which we can use if we're given displacements. Since we're given positions, we're going to use the first equation, which states that delta D is equal to position 2 minus position 1. The S of the GRASP method is to sub and solve This point here, once you've identified what's given, what's required, and you know the equation to use, the rest is easy. So now we're going to sub and solve. We have delta D is equal to position 2, which is 1,200 meters east of home, minus position 1, which is 500 meters east of home. Now, whenever you see a mathematical operation with directions, an alarm bell should go off in your head, and you should ask yourself these questions. This is my alarm bell. Number 1, this question contains vectors. So are these vectors in this equation collinear or non-collinear? And the answer to that is they're both in the east direction, so they are collinear. The second part. So let's just write those down. These are the questions. Number 1, ask yourself, collinear? And if they're yes, you can move to the second part. Same direction? Are they both in the same direction? They're both east. So yeah, they're both in the same direction. If you answer yes to both of these questions, you can proceed algebraically. That means just add them as you would any numbers. So 1,200 meters east minus 500 meters east, we end up with a displacement of 500 meters. Oh, sorry. Always double check we're in this together. 700 meters east. And we don't have to put a reference point because we're finding displacement, and displacement doesn't require a reference point. Okay, the final step is to paraphrase. The final step in the grasp method is to paraphrase, give an answer. Therefore, the displacement is 700 meters east. Perfect. Okay, let's try a second example. Sample problem number 2. What is your displacement if you walk from your school, a position of 500 meters east of home, to the mall, a position of 1,000 meters west of home? So now we're going from the school to the mall. So we're starting here, position number 1, and we're ending up here, position number 2. Okay, let's use the grasp method. Now when you do the grasp method, you don't have to write out these words. In fact, you don't even have to put the letters, but you have to follow the grasp method. You have to write down what is given first, what is required second, and what equation you're going to use. If you abandon these steps, your chances of answering the question are greatly diminished. After each consecutive step you abandon, you will become farther and farther from finding the correct answer. So let's start with what's given. We're given an initial position of 500 meters east of home. And notice I just put this little half arrow. That's kind of my style. It's acceptable in the land of math and physics to do so. We're also given a final position, D2, of 1,000 meters west of home. They want us to find our displacement. So find delta D. If we analyze, since we're given positions, we know that displacement is equal to final position minus initial position. Okay, And now we can sub and solve. That's 1,000 meters west minus 500 meters east. Okay, folks, an alarm bell should go off. Hopefully, this equation triggers you to ask yourself the same two questions. First question, are these quantities collinear? We have 1,000 meters west and 500 meters east. Are west and east collinear? I'll give you a minute to think about that. What I'm asking you is, are west and east located along the same straight line? They are. West and east are located along the same straight line, so these two vectors are collinear. Now ask yourself, are they in the same direction? And it's clear that they're not. West and east are in different directions. In order to proceed algebraically, they have to be in the same direction. So we have to write 1,000 meters west and 500 meters east in the same direction. How do we do that? Well, we know from up above that we can actually change the direction by changing the sign of the vector. So let's do that. You can change both of these to west or both of these to east, and it does not matter which one you choose. You will get the correct answer both ways. You will find a more practical approach when you do this by trial and error and by practice. I'm going to change both of these vectors to west. So the first one remains unchanged, 1,000 meters west. Now instead of having negative 500 meters east, I'm going to change the sign to positive, which changes this direction to west. So we end up with plus 500 meters west. Now they're both in the same direction. We have 1,000 meters west plus 500 meters west. So proceed algebraically. When you do so, you end up with 1,500 meters west. Therefore, the displacement is 1,500 meters west. Now, always look back to the diagram. In the first example, we started at a position of 500 meters east of home and went to a position of 1,200 meters east of home. If you find this distance, it is equal to 700 meters, just like our calculations proved, and in the east direction. Now, what about if we started from our school, we'll change the color so it's more visible, from our school and went to the mall? Well, we can see by the diagram that we ended up traveling a displacement of 1,500 meters west. Always use a diagram or examine the question using common sense and then attempt to prove it mathematically. What you do mathematically should be in line with what you do algebraically or what you envision in your head. Okay, these two must make sense, and that's the beauty of physics, is that you should be able to justify or prove all of the things that you've been kind of understanding or observing about the universe on your own. Okay, let's do a third example. When camping, you decide to walk 650 meters north and then another 400 meters north. What is your total displacement? So let's write down what's given in this question. We're given 600 meters north. There's a magnitude and a direction. Then there's 400 meters north. Another magnitude and direction. The unit of measure is the meter. Now notice, they don't give us any starting or reference point. So though these have directions, they are vectors, but there's no reference point, so they're not positions. So these quantities are displacements. We're given our first displacement of 650 meters north, d delta d1, and our second displacement which is 400 meters north. Okay? And what's required is our total displacement. And to find a total, you just add them up. Delta D1 plus delta D2. We can sub and solve. We have 650 meters north plus 400 meters north. Now, ask yourself the two questions, since these are vector quantities. Number one, are they collinear or non-collinear? North and north are collinear. Number two, are they in the same direction? Yes, they are. So let's proceed algebraically. Just add these up as you would regular numbers. We end up with 1050 meters north. Therefore, our displacement is 1050 meters north. Okay. So we learned how to add collinear vectors graphically. Or rather, we learned how to add them algebraically, but now we're going to learn how to add them graphically. There's a second way we can do these. You can decide at the end which method you prefer. I personally prefer the method that we just already did, even though I love to draw. I don't always prefer to do it graphically, but some of you may actually be visual learners and actually prefer to add vectors graphically. So I'm going to take out my bars of memorization, and we have this statement that says, vectors can be added graphically in a strategy known as tail to tip. Okay, the best way to examine this is by doing a sample problem. So let's try this. A dog is practicing for her agility competition. She runs 80 meters west to pick up a ball and then carries the ball 27 meters east and drops it into a bucket. What is the dog's total displacement? Use vector diagrams. Okay, so we're going to write down what's given. The dog runs a displacement of 80 meters west, 80 meters west. And then, that's our initial displacement. And then our second displacement is 27 meters east. So you can kind of picture the motion of this dog in your head. First traveling 80 meters west, and then changes directions and travels 27 meters east. So we want to find out where they end up with respect to where they started. So what we want to find out is the total displacement, which would be 80 meters west plus 27 meters east. Now, you could do this algebraically. Switch the directions and then add them in your calculator and then find the answer. But we're going to do it graphically. When you do it graphically, you need a couple of things. First of all, you need to show me the reference coordinates, north, east, south, and west. Never eat shredded wheat. Remember that. You also need a scale. We're going to be drawing these to scale on our page. So we can't draw 80 meters on a sheet of paper. So we have to choose a scale that allows us to draw these efficiently on this piece of paper. So I'm going to choose a scale that says 1 centimeter is 10 meters. Okay, let's start. Take out your ruler. By the way, folks, this will only work if you do your best to draw a pretty accurate drawing. And if your drawing is not accurate, then your answer will not be accurate. So take out your ruler, and we're going to draw a directed line segment that's 80 meters west. So I'm going to start from here. I'm using a ruler, trust me. And I'm drawing a line that is 80 meters west. So according to my scale, it's 8 centimeters long. And I'm going to label it delta D1, 80 meters west. This vector has a tail and a tip. And we're going to add the second vector to it in a strategy called tail to tip. So I'm going to draw it off to the side. Don't draw it off to the side. I'm going to use the magic of technology to show you. Here's my second vector, delta D2. And it's 27 meters east, or 2.7 centimeters. We want to make sure that we draw this, but write down 27 meters east. So this vector here has a tail and a tip. So we place these two vectors together, tail to tip. So I'm going to place the tail of this vector to the tip of the first vector. And I'm going to line them up as best I can. Okay, this is what we do when we're drawing vectors graphically. We line them up tail to tip, starting with one, and then you add the other. It actually doesn't matter which one you draw first, because when you add things together, the order in which you add them does not make a difference on the answer. Okay, speaking of the answer, if I've placed these tail to tip, how do I now find the answer? Well, the answer is the straight line that joins the tail of the first vector. Choose a nice different color. The first vector is here and its tail is right here. We're going to draw a line that joins the tail of the first vector to the tip of the last vector. Okay, it's a little too close for you to see any difference. Here's the tail of the first vector, and I'm going to draw a line to the tip of the last vector. Your line should be perfectly straight because you've used the ruler. Now that's our answer. This is our total displacement. So what do I write down? What is my answer? What's my total displacement? Well, take out your ruler, measure the length of this line, measure it in centimeters, and then convert it using your scale. If you measure it, you end up with a line that is about 5.3 centimeters long. If you convert that using your scale, you end up with 53 meters. Now look at the direction. The direction always goes from the tail of the first to the tip of the last. Okay, I'm actually going to write that down. From the tail of the first. Let me clean that up. Tail of the first to the tip of the last. So it is pointing from here to here, which is west. Okay, doing that drawing will give you full marks. You got the correct answer using the graphical strategy known as tail to tip. I just want to prove that we could also do this mathematically. We wrote down the statement, 80 meters west plus 27 meters east. Let's add that algebraically. These are collinear vectors. They're located along the same straight line, but they're not in the same direction. So I'm going to change one of them. We have 80 meters west, but then I'm going to change this to negative west, because 27 meters east is the same thing as negative 27 meters west. Now, because they're collinear and in the same direction, we can punch these into our calculator. 80 minus 27 is 53. And the direction we have is west. So we've proved that both the graphical strategy and the algebraic strategy give us the same answer. You might have a preference for one or the other. Though I love to draw, I also love mathematics, and I tend to prefer the algebraic method. We have some homework questions for you to try as well. There is an LMS quiz that I will direct you to complete. Good luck.